Hey everybody, got another Ghetto demo apparatus here for you to look at. It's something that I actually learned something from in the process of figuring out how it works. It's something about basic transformer design that I had known about for a long time, but had never really thought about it much or even considered why. And we're going to have a look at this thing and see how it works and what we can learn from it. Okay, so this thing is labeled as demonstrator leakage reactance. First, let's look at the power cord. Much better condition than the one that was on the synchro resolver apparatus. This one is a twisted pair, kind of antique looking. Even got a genuine antique plug on the end of it. Look at that. Real dodgy stuff. Anyway, that goes into this transformer right here, which has, looks like the original primary coil is still there on this, on the iron core, but then the secondary is this 10 gauge wire wrapped around with, looks like 10 or 11 turns on there. And then it's really heavy. So the secondary goes through here and then comes here to this twisty-turny little shunt resistor right here, conveniently wrapped up and going back on itself to prevent any kind of magnetic coupling. So it's a non-inductive resistance. And then the other side just goes right here to this banana jack and then going into the coil on this other magnetic core. And this whole magnetic core, this is like the test fixture. It's got these 3 different colored coils here, each the same number of turns, and each one going down to the different colored banana jacks down here. And then there's the black ones, they're hooked up to this air core RF choke down here. So basically these 3 coils, if you hook them up to a meter, then they give, the meters would give you a relative measurement of the magnetic flux going through the iron core, and this one gives you a measurement of the magnetic flux traveling out of the magnetic core and going through the air. And then there's this aluminum ring, and we can see the writing on the bottom explaining how this thing is supposed to work. So terminal is black, leakage flux through the air core coil, and then the different colors, flux through the iron core, and slide aluminum ring to change the leakage flux. So here's the experimental setup. We've got the 5 DMMs here, all looking at AC voltage. This one going across the shunt resistor, and then these 3 in the middle are looking at the voltage output from the green, blue, and violet coils. And then this one on the end, that's looking at the voltage coming off of the air core coil, which is going to give us a measurement of the leakage flux through the air. And everything that we measure is going to be completely relative. I'm not having absolute measurement of the current or absolute measurement of the magnetic flux in a certain number of Tesla or Gauss or anything like that. And we're just going to be moving the ring back and forth as we look at how things rise and fall on all these different voltages. Okay, I'm going to plug it in now. And the first thing you notice is how the aluminum ring tends to move from left to right, and that's just because of Lenz's law, where there's, since the activating coil, the primary is right here, and that's where the magnetic field's going to be strongest, and of course it wants to go in this direction where magnetic field is weakest. Now what this ring represents is not just an aluminum ring, it's actually supposed to be a load. Like if you had a secondary coil somewhere on the iron core, you can basically move that secondary coil and move the load, the electrical load, anywhere on the core, and you can see how the different flux densities change depending on the position of your secondary coil. First, let's have a look at this measurement. This gives us a relative look at the current going through the primary on our test fixture, the test core. And you can see, put my load right here, right next to where you would expect the maximum flux density to be, closest to this coil, then that's going to be the current going through it is greatest. Whereas if we move it all the way over here, then the current is minimal right there. Simply because there's, along this path, there's going to be, some of the magnetic flux lines are going to be going through the air and not intersecting into the aluminum ring, not going through it. And so the primary of this does not have to supply as much power to the secondary. Now for these other coils here, we can see how they go up and down, how the flux goes up and down for each one as I move the aluminum ring back and forth. And basically pay no attention to the numbers, the digital numbers. Just look at the little analog scale at the bottom of each LCD, and you can see how for the green one, as I bring the ring close to it and over top, it's at a minimum, bring it far away, it's at a maximum. For the blue one, you can see as I bring the ring over top the blue, then it goes down to about 300 millivolt, and then it starts going back up as I go away from it, back down. So right in the middle, when it's over top of the coil, that's when the flux is at a minimum at that spot. And same thing for the purple one, all the way over here. We're at 246 millivolt and 373 when it's very far away from the purple coil. And I got to unplug it because this thing starts to get hot after a while. If I leave it on for 1 or 2 minutes, it gets to be so hot that I can't even touch it. Now, to explain this phenomenon, we could go into Lenz's law and Faraday's law of induction and all that, but really all you need to know is that in nature, of course, everything wants to occupy a minimum energy state, including magnetic fields. And so if you can imagine riding along a magnetic field line through the magnetic circuit here, and you come across this big, heavy electrical load that you're going to have to drive, you say, whoa, I don't want to do that. I'm going to go around it. And so you can kind of say that some of these magnetic field lines will go around the iron core or around the aluminum ring, and some of them, you know, instead of going around and then back into the iron core, they just skip it entirely and go back down this way through the air gap. But anyway, what that means is less magnetic flux in the iron core wherever the aluminum ring is, or wherever the secondary coil is for your electrical load. Now let's have a look at the voltage coming off of this coil, and for this particular measurement I'm going to have to use a variac to maintain a constant current on the primary, because it is very sensitive to the varying current that we see when I move the ring back and forth. So I'm going to turn it up right now to till we see 35 millivolts on the primary side. And then over here with the ring over top of the green coil, we can see we're looking at about 300 or we'll say 0.3 volts on there. 0.3 volts coming off of this. Now I'll put it over the blue coil, and again there's 35 millivolts on the primary, and right here we got about 0.7 volts of magnetic flux, relative magnetic flux measurement there. Put it all the way on the end here in the purple. Again, raise the primary to 35 millivolts. And that, again, that's just 35 millivolts on the shunt resistor. And so this one is now giving us 0.8 volts. Let me turn that down. And already prepared a sheet here. Just to review, constant 35 millivolt on the shunt resistor, and then depending on the ring position, we could see this coil is putting out 0.3 volts or 0.7 volts or 0.8 volts. And we can have a look at some flux lines. So the ring all the way on the left basically, if you imagine that you're a magnetic flux line and you're being forced, you're being generated at the primary coil, and then you come across the secondary load here, you say, well, I'm already there, might as well keep on going. And so basically the magnetic flux lines, they just have nowhere else to go. They have to go through the secondary coil. And so that results in minimum leakage flux through the air, because all those magnetic flux lines, they're pretty much forced to go through the secondary load. Now, if we put that secondary load very far away from the primary coil, then they kind of get lazy and they say, whoa, I see a bumpy road up ahead. I don't feel like going there. I'm going to take a shortcut and basically be like an electron, take the path of least resistance. And so those magnetic flux lines, they go through the air gap here and go through this coil to generate a higher voltage. So what have we learned from this? Well, basically it's a really bad idea to have a transformer with such a huge iron core and a lot of space in between the primary and secondary coils. You want to have everything as tightly compact as possible, like 99% of all transformers that you're ever going to come across, where these, something like this, with primary and secondary, or all coils basically, all wrapped around the inside portion of the E frame, the E/I magnetic core frame. There would be a few exceptions, of course, where you have primary and secondary separately wound on two different bobbins and then individually stacked in the iron frame. But again, very tightly packed within the middle of this E. And even if you do see special application transformers like this for audio, very low noise audio quality transformer, even here the primaries, the primary coil is split up among both of these bobbins. So everything is very symmetric, and you don't have primary on one side and then all the secondaries on the other side. And one last drawing, just to reiterate, here's something that you might see in a physics textbook, or maybe in a physics lab that you would do, where you stack different coils onto an iron core and you get your different turns ratios and all that. And but basically, you know, that has primary on one side, one or more secondaries on the other side, and clearly there's lots of room for leakage right here, especially if any one of these are heavily loaded. Then there's going to be even more leakage going through here, and that heavy load, even if it's just on one of the coils, would affect the performance, the voltage output on the other coils. And of course that would happen anyway, because of how the primary itself gets loaded, and you have to take into account the series resistance of the wire. But that's a different story. We're just focused on leakage, the magnetic leakage outside of the iron core. And so here's the better construction, of course, all coils wrapped one on top of another within the E frame to maximize that magnetic flux going through the iron core and going through every single turn of every single coil. So that's the demonstrator of leakage reactance. Really good demo of a basic concept about transformer design that you may not have ever considered before. So please give this video a thumbs up if you learned something. I know I did. Bye.